Hi, everyone.
Hi, Julia. Thank you so much for joining us again. What are you going to be teaching us today?
We're going to talk about my favorite topic, finding life in the universe. How do we do it?
This is a great topic. I'm sure most people have always wondered about aliens.
So, first off, what do you think about life out there? Do you think there is life out there? Do you think we're alone? Where do you think it is? Where do you think we're going to find it? And how are we going to find it? So, I want you to think about this for a moment. We're going to talk a little bit about how do you even know something has life? What makes it a good place to look for life? So we're going to introduce a new word, habitability. And NASA calls it the potential to have habitable environments hospitable to life. There's a lot of big words in there, so I'm going to break that down. We need the right conditions to be able to have water and air, and hopefully some things on it grow to have life. So we know around our star, we have something called the habitable zone. So remember, our star is this yellow one in the middle here. These are other kinds of stars. And we're gonna look over at this kind of blue ribbon called the habitable zone. So Earth is right here in the blue ribbon. And that's part of what we call the habitable zone. If Earth was too far in, too close to the sun, it would be too hot to support life. If it was too far away, it would be too cold to support life. So we're kind of just right. We call this also the Goldilocks zone. Not too cold, not too hot. It's just right for liquid water. And we know, scientists believe that liquid water is key to life out there, or life as we know it. So we're trying to find habitable zones around other stars. If you have a big hot star, you need to go farther away to have it be habitable. Otherwise, it's just too hot. If you have a small, cool star, you need to be actually a little bit closer to feel the warmth of that star. So this is probably the most complicated thing I'm going to show you today. So a lot of people think maybe places like Mars might be good for life, and we're going to talk about why that might not be the case. Okay, so this is, again, the most complicated graph I'm going to show you today. We're going to talk about water and how that water is on Earth. On Earth, we have water that's in the solid form here, with representing ice, liquid in the form of water, and vapor, say, in the form of clouds. And it's because we have the pressure of an atmosphere, keeping the ability to have it be liquid.
Because essentially, pressure is just the weight of the molecules in the atmosphere pushing down on us. The more atmosphere there is, the more molecules there are. And one of the things holding water together in liquid form is that weight.
Right. Also, we have the right temperature. So on this side of the graph, there's pressure, high pressure up here, low pressure here. So the more atmosphere you have, the more pressure. And we have a range of temperatures. And I do apologize, this is a little bit advanced for you young students, but bear with me. So temperature, if we have low temperature, we're gonna have ice. If we have high temperature, we're gonna have water in the form of gas. Like when you put a kettle on the stove, the vapor comes out, right? And if you're somewhere in between, you're gonna have liquid, like our oceans. So Earth sits somewhere here. We've got an atmosphere keeping the pressure in, keeping our water mostly in the liquid form, but when we get too cold, it turns into a solid, and when we get too hot, it turns into a vapor or a gas. So Mars is colder than Earth, and it has a little atmosphere. So it doesn't actually get really much into this liquid phase on this graph. We want to be more into this green part here, but we know Mars's pressure is lower. That's why it's lower than Earth here. And we know it's cooler than Earth. That's why it's to the left. Hopefully that makes a little sense. But we're going to maybe skip forward because this is hurting my brain, and I don't want to hurt your brain. All right, so that was a little bit about liquid water and why it's important and why we need a few things to have liquid. We need an atmosphere, and we need the right temperature. So not too close to the star, not too far away. Hopefully we can all get on board with that. But in our solar system, where should we look for life? Is there good places to look for life in our own neighborhood? So we're going to talk about 4 places: Europa, Enceladus, Mars, and Venus. Europa is a moon of Jupiter. The next one is Enceladus, a moon around Saturn. These 2 moons are icy. And Mars, a planet, and Venus, another planet. I just want to mention that these images are not to scale. So we know Mars is a lot smaller than Venus, and these 2 moons are much smaller than these planets. But I just wanted to show you the pictures of these planets and moons. So Europa, Enceladus, Mars, and Venus. These are kind of places that scientists have been thinking about looking for life. Here's a close-up of Europa, this icy moon of Jupiter. It is so pretty to me. Look at all of those crisscrossy lines. So what's interesting about Europa is that it's got an icy shell. But underneath Europa, they think that there is a liquid ocean. And we just talked about why having liquid water is really important for life. As we know it, all life that we know of uses water. Let's zoom into the surface of Europa. Just look how cool that is. And what we notice is that we don't see anything like craters. We see a lot of these cool lines. And scientists believe that the ice is melting and refreezing and moving, kind of like plate tectonics here on Earth, which means that there's something going on underneath. It's got a secret. And we know all life requires water. Everywhere we find water on Earth, we find life. So do you think that there could be life underneath the icy shell of Europa? So here's an image of what we think Europa looks like. So that surface, all those crisscrossy lines, we call that the chaos features. And then they think the ice layer is pretty thick. And underneath that, there is an ocean. And then underneath that is perhaps a rock interior. So in deep down, kind of like how Earth has a core, Europa also has a core.
So it has a big ocean just like Earth does?
Yeah, it's just like our ocean, but we don't know anything about this ocean. Maybe a few things we can figure out from observing this moon.
But if it's that far down beneath the ice, there's going to be no sunlight.
But we know deep down in our ocean, there's places that don't have any light, but we still find life around them. So these are images from our own ocean. Down at the bottom, we've sent submarines down there to take these videos and pictures of these crazy places called hydrothermal sea vents. They're kind of like mini underwater, kind of like volcanoes, sort of. Now, these places are crazy. It's super hot water coming out of the bottom of the seafloor, making these kind of towers that look like this bottom left image here. You can see the hot liquid spewing out. And on this upper right image, you can see we study these quite a lot because they're super interesting. We have an instrument going in, probably detecting the temperature of what's coming out of these hydrothermal sea vents. And these things are so far down in the bottom of the ocean that no sunlight gets there. But we see abundance of life there. We see these crazy kind of crabs on the right, bottom right picture here. We see these things called tube worms. There's probably little shrimps that live around here. It's a crazy, what we call ecosystem that can survive without any light. So do you think we could find something like this at the bottom of Europa, underneath those oceans? Maybe. That's what we're hoping to find. Okay, the next place we're going to talk about is Enceladus, that moon around Saturn that has these beautiful lines, kind of like Europa, but they're a different color. They're more of a light blue. And we're looking at the South Pole region of Enceladus. It's also an icy moon. And again, we do think that there's some secret underwater, under ice ocean happening, but we don't know too much about it. But we do know that this area here, these blue stripes, it has a cool name. They're called the tiger stripes. And it's doing something super crazy. It's spewing out water from these areas. I'm going to show you another picture of that. So from the South Pole, it's spewing out water. And I'm going to tell you something. I have a secret name for this moon. I call it the PP moon. And I'll tell you why I call it PP moon. It's because it looks like it's peeing. From the South Pole region are these water geysers that are coming out, spewing out into space. So we're trying to send spacecraft there, perhaps, to capture some of that stuff coming out, that water coming out. Because we want to see if maybe it has life underneath the icy layer. And instead of drilling down to see it, maybe we can fly through those plumes, those water geysers. Yeah, so that's probably one of my favorite moons.
I think it's my favorite moon now too.
Moving on, Mars. So we've talked about a little bit about Mars, and scientists really want to send humans there one day. It's the red planet. But there's evidence that there is water on Mars, but perhaps not in the liquid form like we have seen on Europa and Enceladus. Because remember, Mars is a little too cold, and it doesn't have a great atmosphere. It doesn't have enough pressure to keep the water on the surface liquid. It's mostly in what we call the ice form. You can see at the top here, we have this polar ice cap. It's made from frozen H2O water and frozen CO2 carbon dioxide. So Mars gets really, really cold, like minus 100, 200 degrees Fahrenheit, pretty cold. Too cold for humans to live without a lot of gear and protection. So yeah, how should we find life on Mars? How are we gonna do it? We'll talk a little bit more about that in a second. Another place that people in the past have thought about life is in the clouds of Venus. So Venus is a really hot planet. We talked about we can't be too close to the sun because it's too hot. We can't be too far away because it's too cold. So Venus and Mars kind of straddle the habitable zone. Venus is a little too hot. It can get up to about 860 or 900 degrees on the surface. It's so hot, it will melt lead. Certainly not a place to look for life as we know it, but perhaps in the clouds, maybe you could have some weird forms of floating life around there. We don't know. It's probably not the number one place to look for life, but a cool place in our solar system to think about life. Or should I say hot place. It's much cooler in those clouds. Maybe there's some form of weird Venus bird. Who knows? So we should study Venus a little bit more to find out. Most likely it does not have life, but you never know till you go. Okay, so what about life beyond our solar system? We talked about perhaps places in our solar system that we could look for life. But what about beyond our solar system? We talked a lot about exoplanets out there, planets that orbit other stars. Do you think we could find a planet around a star that perhaps is like Earth? So how do we detect life out there? By looking really, 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 really carefully.
And I guess you first have to know where to look, so you first have to find an exoplanet, and we can actually see them.
Right, these are exoplanets around another star. So we're seeing planets around another star, and that blows my mind because really, when we're detecting these exoplanets with those methods we talked about, you're not actually seeing the planet. You're seeing the effect of the planet going in front of the star or making the star wobble. But this is a real image of other planets. And I'm going to talk next about why we want to see exoplanets.
Because just seeing an exoplanet doesn't mean there's life. How do you know a planet has what it takes to be habitable? What do you look for?
We want to see rainbows.
Why rainbows?
We want to see the atmospheres of other planets to see what's in them. And the way we do that is using rainbows. When we have a gas like our atmosphere, we have oxygen in our atmosphere. Every time we take a breath, we're breathing in not only oxygen, but nitrogen, a little carbon dioxide, perhaps a little methane, things like that. We want to figure out what is in an atmosphere. We know the atmospheres of Mars and Venus are mostly carbon dioxide gas. And we know there's probably not life on those atmospheres. Did you know that life can change the atmosphere? So why is it that Earth has oxygen? It's because we have plants that create oxygen. We have trees, we have plants, we have bushes. So we have plants constantly pumping out oxygen, and we have species like mammals who breathe in that oxygen. We know that life can change an atmosphere. So we think that probably Mars and Venus don't have life on them. Maybe if they do, they're small microscopic life in the clouds or on the surface. So we want to find some weird atmospheres on exoplanets. And the way to do that is using rainbows. So I'm going to try and explain a really hard scientific concept to you using rainbows. Okay, let's try this out. We have our gas. Let's pretend this is our atmosphere. When we have that light from a star kind of going through the gas, and we put that light through a prism, we see these tiny little lines, these black lines. We call them absorption lines. And those lines are different depending on what kind of gas you have. So if we were to look at the spectrum, I'm going to use this word spectrum. Actually, I'll just say rainbow. When we look at the rainbow of Earth's atmosphere, we see these lines. You need very special prisms to do this. So you probably can't do it with just your regular prism. To see these lines we want to see the lines of oxygen, perhaps nitrogen, carbon dioxide, the things that we know Earth has. Earth's going to have lines that represent those things in our atmosphere. Mars is going to have mostly carbon dioxide. Same with Venus. So those lines are going to look different. They're going to be different space. And I'm going to show another image. So we see every single element has different lines that are in different parts of the rainbow. So on the top one, we see hydrogen, which is a gas. It's lighter than helium. So we know hydrogen has a line, 2 lines in the blue and 1 in the red. Helium has a bunch of lines kind of throughout. Oxygen has a bunch of lines as well. Neon, look at all the lines that neon has. So every single element or molecule has a very special, what we call fingerprint. It's kind of like a barcode. So you know when you go to the grocery store and get your barcode scanned, everyone's going to be a little different because the price is different, right? So every gas that we have in an atmosphere is going to have different lines. And this is how we're going to see what it's like on another planet around another star. And to me, this is the coolest part of science, is looking at rainbows and looking at them closely enough to be able to see what is in that atmosphere without even going there. I don't know about you, but I think that is super duper cool. And here's a real picture of our star using rainbows. So we see that our star also has some features, and we can see the lines that look like this. So I just wanted to show you kind of what it looks like in real life. So we want to look for these lines, or if you are a scientist, you look for these dips here, because that lines up with these lines. So I know this is kind of a hard thing to think about, so I'm going to keep moving. So that would be really cool to find signs of perhaps what we call biosignatures, signs of life on other planets. But this technology, we're not quite there yet. But what about aliens? What about signs of extraterrestrial intelligence? signs of technology. So do you think that there are aliens out there that have technology kind of like what we have? So we use things like cell phones all the time. We're using our computers. I'm broadcasting this through the internet. So we have all of this technology, and some of our technology creates waves. Waves kind of like light. We are sending out light waves all the time. We're sending out powerful radio waves. Have you ever seen a radio tower? So that is creating a sign of our technology that's leaving the Earth. So we might be detectable by our radio waves to an alien out there. But what about aliens that are trying to maybe send us a message, like ET? Do we think there are ETs out there phoning home? So we've been using radio waves for about, 100 years or so. And those radio waves are continuing on in space, out and out and out. And we might be detectable, but we're also listening for radio waves from aliens. And that's what I do. I mentioned we emit powerful radio waves. So I don't know if anyone is from the Bay Area, but this is a high-powered TV radio tower on the left screen here. We call this Sutro Tower. It's in San Francisco. On a clear day, I can sometimes see it from my neighborhood. And this is a very powerful radio tower. So these are emitting powerful radio waves. And we are also using big radio dishes like the one in the middle to send out these radio pulses, kind of like radar, or how a bat does echolocation. It does a chirp and it listens for the chirp back to know if there's a wall in front of it or perhaps a yummy mosquito that it wants to eat or something like that. So we are sending out these high powerful pulses of radio waves that we're trying to see if there are any nearby asteroids. Why do we want to do that? Why would we want to send out high-powered radio pulses out around Earth? We don't want to be smashed by an asteroid. We don't want to end up like the dinosaurs. So we are sending out high-powered pulses to just check out what's nearby, kind of like radar or sonar. We want to make sure that our neighborhood doesn't have any big asteroids in it because we don't want to end up like the dinosaurs. So we send out these big powerful pulses. Perhaps an alien will be doing the same thing to make sure that they aren't being destroyed by nearby asteroids. And last thing that we send out are these high-powered lasers, and they're pretty powerful. So these lasers can outshine the sun if you're looking kind of right at them. So these are easily more detectable than just without sending them. They're pretty detectable. So these are the ways that Earth is sending out radio waves and in light waves that are perhaps detectable by aliens. Now, I bet you didn't think about that when you listened to the radio.
So we know we're sending out these signals into space that aliens can see or hear. So we're looking and listening for signals that maybe aliens have sent, right?
Right. So we are trying to detect signs of technology, ET technology, by using these powerful radio dishes. So the one on the right is one that I observe on. It's called the Green Bank Telescope. This one is in West Virginia, and it's the largest steerable structure. It's bigger than the size of a football field, and you can steer it to point around different places in the sky. So we steer it because we want to see if perhaps there's a star that has an exoplanet around it.
And maybe that exoplanet has intelligent life that has technology.
Maybe we should listen to see if they're sending out any cool radio waves. Maybe they've got some cool alien TV show, MTV or something, that we want to pick up.
So your telescope is one of the ways we listen for those signals?
Right. So we use big radio dishes like that. And this one here on the bottom, this is an array in New Mexico, that when you combine a lot of little dishes, you can almost create a bigger dish by combining the signals from those little dishes. And the last way we look for life out there is we're looking for those laser pulses. So again, using those ground-based optical, those regular telescopes. This is a fancy telescope. We're looking for those laser signals. So those are the ways that we look for life out there. Did I just blow your minds? This is how my brain feels right now. I know we talked about a lot of things.
But that was amazing. I learned so much about life out there.
So I want to say thank you so much.
And thank you, Julia, for taking the time to teach us. To all of you in your rooms, thanks for tuning in, and we will see you next time.
All right, bye everybody.